Hi, I'm Katie Rocci. I recently graduated from the University of New Hampshire, and I'm now a master's student at Colorado State University. I did my senior thesis at UNH on methane isotopic composition up at Swordal and Meyer in Abisko, Sweden. So this research is kind of a compilation of a couple years of research on this topic. So our research is called Methane Carbon Isotopic Composition Reveals Changing Production Pathways Across the Gradient of Permafrost Thaw. I'd like to thank all my co-authors. They were all super important to making this work possible. Okay, so we know that the world is warming, and the Arctic is warming at twice the rate of the rest of the world. This is important because the Arctic has these areas of permafrost, or permanently frozen soil, that are thawing with the warming of the Earth. Now, as these areas thaw, they make these really wet environments that promote methane emission, because methane is produced anaerobically. Now, methane is a greenhouse gas that's 25 times stronger than CO2, and therefore is really important feedbacks to climate change. So Swordal and Meyer, where we were working, is an area of discontinuous permafrost thaw, so we can be used as a proxy for how things are going to change in the future. We also know that methane production moves from hydrogen-trophic methanogenesis towards acetoclastic methanogenesis as thaw progresses, and this can be understood by looking at methane isotopes. So our question is, how does methane isotopic composition vary along a thaw gradient over the growing season at Swordal and Meyer? So this is our study site, Swordal and Meyer. We collected data from June to September of 2013, 2014, and 2016. Here is transect B, one of our thaw transects at Swordal, and it was a beautiful place to work. And then here is me collecting pore water. So what we do is you take this long metal tube called a sipper, you stick it in the ground, and you take up pore water at different depths. I take these pore waters back to our lab, measure the methane concentration on our gas chromatograph, and then measure the delta 13C, or the isotopic composition of the methane, on our quantum cascade laser. Then we used JUMP to analyze our data and assess the significance of seasonal and site patterns and their interactions. Okay, so this is what our thaw gradient looks like. So PW5 and PW4 are our two driest sites, and they're dominated by sphagnum moss. PW6 and PW3 are our next wettest sites, and they're dominated by Areophrum vaginatum. And PW1 is our wettest site, and it's dominated by Areophrum angustifolium. So if we come down to this graph here, x-axis is going to be date, y-axis is delta 13CH4, so the methane isotopic composition. And we know that there's a shift in the dominant production pathway around -60 per mil. So it's acetoclastic when it's less negative than that, and hydrogen-trophic when it's more negative than that. So the first thing we'll notice is that PW1, our wettest environment, is very different from the others, and in fact significantly different from the other sites. And this is because if we look at this depiction of Areophrum, we can see that O2 is brought down to its roots to keep it alive. It lives in this wet environment. Then the roots exude acetate, and then this acetate is then transformed by microbes into methane, which can then be really efficiently brought into the air. Because Areophrum has these arrancamous tissues, so it kind of acts like a straw, so the methane can get from this wet environment up to the air without being oxidized to CO2 first. So that's why PW1 is kind of different, and we kind of expect that. But a really interesting thing is this shift from hydrogen-trophic methanogenesis early in the season for these intermediate sites up to acetoclastic in the later sites here. And then for PW5, this purple line here, it's actually a significant shift from earlier in the season to later in the season. This is even more clear on our second graph. So once again, x-axis is date, y-axis is alpha C, which is the fractionation factor for carbon and methane relative to CO2. And this one shifts at 1.04, so it's acetoclastic below that and hydrogen-trophic above that. And you can see the hydrogen-trophic quickly shifts to acetoclastic here, right in that same area here. So it's really clear pattern. So in conclusion, our minerotrophic thawed areas, so PW1 are really wet areas, have this consistently acetoclastic dominated signature, which is as expected, it has been seen before. But what's novel here is that these intermediate thaw stages are shifting later in the season towards acetoclastic methanogenesis. And this is really interesting because it has really important implications for climate change, right? So we expect this site to get warmer and wetter, and we expect this to promote more thaw and greater methane emission and heavier isotopic ratios, and to also increase the growing season length, which may shift isotopic ratios more towards acetoclastic methanogenesis and potentially result in more methane emission, which has really important feedbacks for climate change. Thank you.